Every great project, whether you're building a house or a molecule, starts with a blueprint. And in chemistry, our blueprint tells us two crucial things. What are our raw materials, and what's the final thing we're trying to build? Let's take a look.
Okay, so over on the left, these are our basic building blocks. We've got benzaldehyde, which is known for its cool ring-like structure. And then we have acetone. Yeah, the same simple chemical you'd find in nail polish remover. And on the right, that's our goal. That's the bigger, more complex molecule, dibenzalacetone. The whole challenge here is figuring out how to snap these pieces together in exactly the right way.
Now, you can't just toss your building blocks in a bucket and hope for the best, right? You need a master plan. You need a specific method. In the world of chemistry, that plan is called a reaction, and the one we're going to use is a classic known as the Claisen-Schmidt condensation.
I know, it's a mouthful, but don't let the fancy name scare you. When you break it down, it's pretty simple. All it really means is that we're using a base, think of it like a chemical kickstarter, to convince our aldehyde, the benzaldehyde, to link up with our ketone, the acetone. It's basically a forced chemical introduction that ends up creating a brand new, much bigger molecule.
And just like with any good recipe, the proportions are everything. You can't just wing it. For this particular build, the ratio is absolutely critical. We need exactly 2 molecules of benzaldehyde for every single molecule of acetone. It's a precise 2-to-1 deal, no exceptions.
And here it is, the whole process written out in the formal language of chemistry. You can see our 2 benzaldehyde molecules combining with that 1 acetone. And what do they make? Our final product, dibenzaldeacetone. But hey, look closely. Notice that little extra something on the end? 2 molecules of water are also created. They're kind of like the leftover sawdust from our construction project.
All right, so we've seen the blueprint. We've got the master plan. Now let's zoom in, way in, down to the molecular level and watch this assembly line in action. It all goes down in 4 very specific steps.
Step 1, we've got to activate one of our building blocks. The base comes in and literally plucks a tiny hydrogen atom right off the acetone molecule. This leaves the acetone with a negative charge, turning it into what we call an enolate ion. And that negative charge makes it really unstable, super reactive, and just itching to connect with something else. It's like preparing one end of a Lego brick so it's ready to snap firmly onto another piece.
And here we go, the first real connection. Our supercharged enolate ion does not waste any time. It immediately launches an attack on a benzaldehyde molecule, latching on and forming the very first bond between our 2 starting materials. This is it. This is the moment they officially join forces.
So at this point, the new molecule we've made is it's a bit awkward and unstable. To fix that, it reorganizes itself by kicking out a molecule of water. That's a process we call dehydration. Getting rid of that water allows it to form a nice, strong double bond, which locks the new structure in place. And just like that, we have our intermediate product, benzalacetone. We're halfway there!
So what now? We basically just rinse and repeat. The whole process happens all over again. Our benzalacetone molecule gets activated by the base, it attacks our second benzaldehyde molecule, another water molecule gets the boot, and bam! The final structure is complete. We have successfully built dibenzalacetone.
Okay, so that's the invisible molecular dance that's happening on a scale we can't even see. But what does all of this actually look like in the real world, in a lab? Let's zoom back out from the atomic level and see how chemists turn all this theory into something you can actually hold.
In the lab, it's a really methodical process. First, you just combine the starting chemicals. Then, you slowly add your base, which is the catalyst that gets the whole party started. After that, you just have to wait and let that 4-step molecular dance do its thing. And pretty soon you start to see it. A bright yellow solid begins to form in the liquid. That is our dibenzalacetone, appearing right before our eyes. The last few steps are really just about cleanup, filtering, washing, and drawing our brand new creation.
So let's just take a step back. We've gone from a simple blueprint on paper all the way through a 4-step molecular assembly line to a real-world lab procedure. So what did we actually make, and what's the big takeaway here?
To sum it all up, it's this simple. We started with 2 basic liquids, benzaldehyde and acetone. We used a very specific master plan called the Claisen-Schmidt condensation. We followed a precise 4-step molecular assembly process, and in the end, we created dibenzalacetone, a brand new yellow solid compound practically out of thin air, or, well, right out of our starting chemicals.
And that really leads to a fascinating final thought.
We followed one very specific recipe today. But what happens if we change the ingredients? What if we swapped out the benzaldehyde for a different kind of aldehyde, or the acetone for a different ketone? Just think about it. What other incredible new molecules are just waiting for us to build them? Thanks so much for watching.